Log on, tune in, find out. Another good idea from Cambridge.
Provocative title of Finding Primes Deterministically.
Yes, well, I'm not sure what's so provocative about it. It's pretty descriptive, but so first of all, let me tell you, yes, so this all started as a polymath project. It was supposed to be massively, it's one of those massively collaborative projects. It was supposed to be. It got, I would say it got only partially off the ground, still enough for a talk, I hope. The referee is forcing us to say who the primary contributors were anyhow, so I might as well say them here. So it would be Ernie Krut, myself, and Per et al. Very well, finding primes. So I literally mean that. Find a prime between 1 trillion and 2 trillion.
1 trillion for 7?
I suspect this. Well, did you check that beforehand?
Did you?
No. But, well, we can test it. With non-zero probability, it will be a prime. And we can test whether a number is prime quickly. I can't, but we can. However, it might not be prime. In that case, you have to come up with another number and check it. And another one, and check it again. Well, how long would that take? If you're satisfied with a probabilistic algorithm, then you can just say there are certainly many primes between 1 trillion and 2 trillion, about 1 over log n of them. 1 over log n of all numbers between 1 trillion and 2 trillion are prime. Hence, in time, a large constant times log n, I will almost certainly hit a prime. And we certainly have got fast algorithms, both deterministic and probabilistic, for checking primality. So probabilistically, the problem is easy. So by fast, people always mean time log n to a power. Are there any algebraists in the audience? Do I need to explain O of notation? All right. One thing, I was not trying to imply anything, but all right. So O of 1 just means a constant. Deterministically, the problem seems, it's surprising, but it seems to be much harder. So I remind you that checking primality, so it has been known for quite a long time that you can check primality probabilistically in polynomial time, but for the last 8 years or so, people have also known how to do that deterministically. So that's otherwise Cahiers and Saxena. So, yeah, so what do we know about the deterministic case? So, people differ about what they like to call trivial, but it's certainly trivial to do it in time n, or n times log to a power. You start to check all the numbers from n up to 2n, one by one, and you know at least one of them is a prime, and the test will tell you. Now, of course, we know a bit more about gaps between primes. We know that there is in fact always a prime between n and n to the n plus n to the 0.525, I think is the current record. So this would be the same thing. It's the same trivial algorithm. You start at n and you start adding 1 or adding 2 if you're really clever, if you start at an odd number. Now, by the same token, with the same silly algorithm, you get one half plus epsilon under the Riemann hypothesis, and you actually get that these are what you would see as a holy grail here, a fast algorithm under Cramer's conjecture. Cramer's conjecture tells you that there's always a prime between n and n plus a constant times log n squared. So if you assume Cramer's conjecture, you are done. Just by the silly algorithm. Start with n plus 1, n plus 2. So, in fact, well, of course, Cramer's conjecture and even the Riemann hypothesis are very hard and open. But one can actually do as well as that, as the Riemann hypothesis result, if you are a bit more clever. So, in fact, unconditionally. And this is, I wouldn't call this trivial at all, but it was the limit of what was known up to now, or what could be got easily from known results. So you can get of n to the 1/2 plus epsilon, because you can compute pi of x, where pi of x is just the number of primes up to x, with accuracy, with an error of less than L, say, in time of x over L. So this is Lagarius and Odliško. And this is by, well, classical but very analytic number theory, contour integration. You have to be clever with this. Now, so how does this result of Lagarius-Odliško imply that you can do it in times of n to the 1/2 plus epsilon? Well, let me first point out, so it will be by the same token that we can do it if we have a stronger result. If we can compute the number of primes in n, comma n plus m, well, m at most n, in time t, with an error of at most, well, an error of 0, say, then we can solve the problem. We can find a prime in times at most t times log n. Why is that? Well, in fact, all that we would need would be not something that tells you the number of primes with 0 error, but just an algorithm that tells you whether there is a prime at all within an interval in time t. Why is that? Well, this is no longer trivial. This is more like nursery school, because we play 20 questions. That is, you know, well, or guess my number. I'm thinking of a number, or there is a number in my set between 0 and 100. Well, is there a number in your set between 50 and 100? Yes, there is a number in my set. Well, is there a number in your set between 50 and 75? Yes, actually. Is there one between 50 and, well, the average of 50 and 75, whatever it was? No, well, so I will, all right, very well. So I will narrow my interval, choose the other one, and go on. And in log n step, I am done. So it's a binary search. Well, binary search means so many things, so let me call it 20 questions. Where, of course, 20 stands for log n. And the same thing works here. You see, at first, you don't want to set your accuracy too low, but you don't have to set it too low, because you know there are a lot of primes anyhow. So setting your accuracy to vaguely square root of n will be enough to be able to let you tell for the first few steps whether you have any primes in your algorithm. And once your interval gets a bit smaller, then you can increase the accuracy a little bit. It's a bit tricky, but you can do it. Actually here, you stop. So this will be 20 questions. but here you stop when your interval is of length about square root of n. Because then, unfortunately, this algorithm does not allow you to, it just depends on x. It does not get much better as the interval gets shorter. However, can we do any better than this? Well, we tried. So what I'm about to write is unsatisfactory from 2 points of view. It's not log n to power time, far from it. It is better than n to the 1/2, but it's not what you would call a fast algorithm. The other reproach is that it has a funny sort of condition. So, well, there will be a theorem that will make the corollary look less funny. So the corollary will be if the number of primes between n and n plus m, where m is some number you choose less than n, is odd, we can find a prime in the interval in time n to the 1/3. But what on earth? I mean, this is the first time I see such a condition, such a result. So why? Because we can compute the parity, that is whether the number is odd or even, of the number of primes between n and n plus n. And then the corollary follows from the proposition by 20 questions. So proof corollary, the proposition. Now, so the wonderful thing about odd numbers is that if an odd number is the sum of two other numbers, at least one of those has to be odd. So you take your interval, there's an odd number, say you ask, in my interval, is there an odd or an even number of prime numbers? If the oracle says even, then you just throw your hands up in despair and you go home. If it's odd, then you're in luck. You know, you will succeed in times n to the 1/3 because you ask the oracle. Well, if I have the interval and I look at the first half, is the number odd or even? The oracle says, say, odd. Very well. So I look at that interval. Now I split it in half. Is a number of things in the first half odd? No, it's even. All right, I will look at the second sub-half of this first half. And I keep on narrowing down. And when I have an interval of length 1, say, and the number of prime numbers in it is odd, then I know that it consists of one number, which is necessarily a prime. Yeah. Very good. So 0 is not an odd number. That's very important. Now, all right, can we do anything other than proposition 1? Already proposition 1 looks as if it could almost do the job, and in fact you can make it, it's fairly flexible. So this is in time, 10 to the 1/3 plus epsilon, and also you can do this if you restrict an arithmetic progression. And one can actually do something. The statement will look a little odd unless the sort of statement is familiar to you already. You can represent the following funny polynomial. So it's x to the p for all primes between n and 2n. So this is an element of z mod 2z x. So you consider it as a polynomial with coefficients in z mod 2z. And it turns out that you can represent this in time less than n to the 1/2 as a circuit of complexity less than n to the 1/2. This is a circuit, meaning just a set of multiplication, addition, etc. operations of size less than n to the 1/2. let me just say, with complexity of n to the 1/2 minus delta, where delta is absolute. And so what follows from this? From this it follows, that well, how long do these operations take anyhow in your circuit? Well, if you take everything modulo a small polynomial, by which I mean a polynomial of small degree, then everything takes constant time. So, in fact, you can tell, let's call this P, can compute P mod 2G, where G is an element of the polynomial ring of bounded degree, or even, really small degree, in time less than n to the 1/2. So the corollary over there is a particular case of the corollary over here, because the corollary over there, which tells you the parity, is exactly what you get from this when g of x is x plus 1. No, because if g of x is x plus 1, then this is just one of two things, one if it's odd and one if it's even. If the number of times is odd or even. X plus 1 just collapses everything in the polynomial. It's a very funny thing, because you would think of this, you could say this polynomial has coefficients that are 0 or 1, so the polynomial with coefficients in z mod 2z determines the polynomial with coefficients in z. Shouldn't that be the end of the story? Well, things don't work out that way. It's a bit counterintuitive, apparently. So even this, we haven't been able to make it yield to us an algorithm for computing precisely, with 0 error, the number of primes between n and n plus n. If we had such an algorithm, then we would have something working, an algorithm for finding primes in all cases in times less than n to the 1/2. Very well, how do we proceed? Well, I will focus just on giving a proof of proposition 1. It's possible to give a proof that is worse than the one I will present. Why would you ever want to do it? Because the worst proof is the proof that gives you a slightly worse bound is actually more robust, and the same proof carries over more easily to prove that. That's why I had 1/2 minus delta there as opposed to 1/3. So the proof I will give has some things that are, if you wish, refinements or particularities of the more classical case. But if you manage to make the proof a little bit worse, then it does carry over. So how do we start? First of all, well, how on earth is it possible that we can compute the parity of a thing, but we do not get to compute the thing? Well, this happens sometimes. What will happen is, in fact, that we will not really be computing the number of primes. We will be computing a different quantity, which happens to be congruent to the number of primes modulo 2. So what is this quantity? Well, in fact, we will be messing around with the divisor function. So by tau, I don't mean the Ramanujan function, I mean the divisor function. Tau of n is simply the number of divisors of n. So tau of 1 is 1, tau of a prime is 2, and tau of n for n square free not a prime, it's always a multiple of 4. No? Because tau of n for n square free is 2 to the number of prime divisors of n. Very well. So what have we got then? We have got then that the sum of tau of n over the square frees This is very confusing. The sum of tau of n over the square freeze where by square free I just mean having no square divisors. This is congruent modulo 4 to 2 times the number of primes between n and n plus m, plus 1 if n were 0, no? Very well, but then so it's if all you care about is the parity of the number of primes, it's enough to compute the sum of tau of n modulo 4. Oh, or in fact, it's certainly enough if we compute the sum of tau of n with 0 error, period. And it should be completely unsurprising that we don't really need this square-free restriction. In general, square-free restrictions are easy to remove. I mean, you need a few more sums, but the number of sums and their length decreases rapidly. So, in fact, it's enough to compute tau of n with 0 error in time of x to the 1 percent. Now, there's a very trivial and very important principle. If you compute an integer with error less than 1/2, then you have computed it with error 0. Why? Well, you have the round function. So this is, I cannot emphasize this enough. In order to feel better about what I just said, let me just point out that some people would say, and I would agree, that one of the guiding principles of Diophantine analysis is that a non-negative integer, is that an integer bigger than 0 has to be at least 1. It's actually related in a sense. And if you keep that in mind and you are not ashamed of that, then you can prove lots of nice things in either case. So, in fact, it's enough to allow. We can allow ourselves an error as long as it's tiny. Or if we don't know how to do things with a tiny error, we can split our problem into subtasks and accomplish each of the subtasks with error less than 1/2. Well, in fact, this should be vaguely familiar to part of the audience. So, in fact, I hadn't seen anything about computing this as such before, but there is a classic problem of giving approximations to this sort of thing with an error that is small as possible, approximations that are generally closed expressions, so things that you can write down. And generally closed expressions are very easy to compute. They take very little time to compute. So this is what's known generically as the Gauss circle problem, though in this case it's a hyperbola, not a circle, as I will draw on the board soon. Is there water in my glass already? Well, that's another sub-problem. So the Gauss circle problem, or really, for this time it's really the hyperbola problem. So in all of these cases, well, I will not even bother to write down the closed expression. So it's basically just the area plus an error. So this is fast to compute. And the error, how much is the error? O of n to the 1/2 is trivial and due to Gauss. Sorry, Gauss. Improving on that is quite hard, or at least it was quite hard. And it's due to several people, but it's the early 20th century. I think Sierpinski had something to do with it. I think there were other people involved as well. So I mean, some of you will have encountered probably at least 2 proofs of this. So there are some very nice proofs using Fourier analysis. If people want to get fancy, then they use Fourier analysis over z squared, and well, you see a Bessel function and you're only half a page. But you can also do it in a much more elementary fashion. And in fact, part of our work on this was inspired by, well, I mean, so actually the first serious math book I got when I was a teenager, in fact, was Vinogradov's Elements of Number Theory. And I cannot say that I remember that, the important bit, but I remembered it from when I had attempted to use it to teach undergraduates. I'm not sure I quite succeeded, but it's this wonderful little book. So the text is trivial, but the exercises are very nice. So yeah, so I don't think that Vinogradov was one of the first people to give a proof of this, but it's the proof in his book. He generally does not give credit even to himself, so it's a bit difficult. It's a proof there that served as an inspiration for part of this work. There are better results than this, but the results that are better than that have much less combinatorial proofs, and so they are harder to adapt. And it's a combinatorial proof of this that we will be adapting. Or not adapting, but some of the ideas here will be inspired by that. So, of course, there are errors here, and this is a huge error compared to 0.5, which is the error we're aiming for. However, the methods are flexible enough that we will be able to split things. I mean, the combinatorial proof proceeds by splitting things into intervals, and that's what we will do. And we will look at things in each such subinterval. But what are these intervals I keep talking about? So, I mean, well, first, it's always helpful to split this sum into dyadic intervals, but then we will split them into intervals of variable length. So, very well. Into dyadic sums, meaning just sums of this form. And then further. Well, how much further? That will become clear soon. But first of all, let me explain. Why did I speak about the hyperbola problem? Where is the hyperbola here? Well, sum of tau of n. So, well, say up to x. This is just a sum, and here you have a 1 for every divisor of n. And here you can do what you always do, or what I always do when I don't know what to do, namely I change the order of summation. And then, of course, here what we have is integral parts of x over d. But what is this then? Well, this sum is nothing other than the number of lattice points under a hyperbola. The hyperbola y is equal to x over d. Yeah, so actually I was very lucky 2 days ago. I was giving more or less this talk in Durham, and there it was pointed out to me they had a projector. Well, there's a projector here, but not quite of the same kind. And I did not have any transparencies, but I had this sort of paper here, so I didn't need to draw grid points at all. But I hope you will forgive my grid, and I hope it will be clear enough that the sum here is just the number of lattice points under here. No, if say that here were at height what 2.7, then the number of lattice points under the curve is 2, the integer point of 2.7. Now, how can we compute this? Well, we can certainly compute this in times O of x by just summing over each term of the sum. If we're a bit more clever, if we just look at the graph, we can do exactly what Gauss did, namely exploit symmetry. We can say, well, this hyperbola has an axis of symmetry here, so the number of lattice points, so this is number of lattice points, well, we can divide this up into 3 regions, 1, 2, and 3. And then what we have is, of course, that the sum, so the sum of tau of n is the number of lattice points in the 3 regions, which is just twice 102 minus 2, because there are as many lattice points here as there are here. And then this is just a square, so its area is very easy. No? So this is just square. So it's enough to compute this. So here you see already right away that doing it in times x to the 1/2 is easy. And actually, this is essentially the same reason why Gauss got an error term of size x to the 1/2. It doesn't go further than that. So, but now the question arises, so how do we do better? How can we compute this quantity here in times less than square root of x? No, and, well, so, or really, in the dyadic interval. Where a is less than square root of x, but we can assume that it's more than a constant times x to the 1/3, because the first x to the 1/3 times a constant term, so we can compute by brute force in times x to the 1/3. Oh, and that's fine, because we will have to spend that much time in the rest of the task, so we can allow ourselves that. So the task that remains is to compute this with error less than 1/2 in time, well, of x to the 1/3. All right, so what shall we do? Well, so by brackets now, by curly brackets, I mean the fractional part, meaning the number minus its integer part. So we have this is just a sum x over d minus the fractional part. Now I claim that the first sum, without any funny signs, this sum can be computed quickly. Why? Sure, Euler-Maclaurin will do it. Yes, exactly. Or your favorite method. I mean, you can also do it. Kepler would already know how to do it, but Euler-Maclaurin does the job quite nicely. So, yes. So we can do this quickly with error. Well, with a completely ridiculous error. We can do much better than this. Let's say error less than this. By Euler-Maclaurin, because we just need, we can of course do definite integrals very rapidly if you get an exact expression as here, and you just need the first 4 or 3 terms actually of Euler-Maclaurin to do this with very high accuracy. Very well, so we have to compute the fractional parts over there. But what are these fractional parts? Well, let us first indulge in a little bit of wishful thinking. Imagine, so x will actually be an integer. So what I'm about to say is not quite true, but imagine that x over d were actually a rational number with small denominator. So what if? Especially, say, x over a, or x over, say, we will split this further into subintervals. So we will split it into intervals of the form where the length will be set later. But we split this into intervals of the form, say, it will be easier if we use n and 0 up to n plus delta 0. Very well. So what if x over n 0 is equal to a over q? Well, this is a fraction with small denominator. Well, then this will actually be very nice. Why? We can expand. If we're clever, we do it around the middle of the interval, but we're not clever because it is a talk. So this is just x over n 0 plus, or this is confusing. So let me replace this by a big N, simply so that you will not think that x is a variable. Times delta. So this is for n equal to n0 plus delta between 0 and delta 0. Part of now here, of course, the variable here is the thing in the denominator. So this will be L of n over n0 third delta squared. So if delta is not too big, this will actually be quite tiny. So we want this to be not just smaller than 0.5, we want this to be smaller than 0.5 divided on delta 0. So for for delta 0, smaller than, let me see how much, it's just a quick computation. Smaller than a small constant is n0 divided by the cube root of n. This is just going to be smaller than, say, 0.01 divided by delta 0. So this will, as we will soon see, pretty much negligible all of the time. There will be a couple of exceptions, but we will point them out. So what's going on here then? So we want fractional parts everywhere. So this is fixed, all right? Delta is varying. But then how is this sort of thing varying? Actually, I sort of lied here. What I want to approximate is not x over n0, it's n over n0 squared. I changed my x to n, just for ease of understanding, and I really want n0 squared here at the bottom. So what happens here? This will just be minus n0 squared, which is minus a over q. So I just have a linear expression. So I start out is 0 to 1. I start out at some given point, n over n0, and then I start adding minus a over q over and over again. No, for all, and let us say that delta 0 is a multiple of q. So each residue class will be represented exactly once for each subinterval of length q. So you have n over n0, then you have n over n0 minus a cubed, goodness knows what that is. But then you have minus 2a over q, minus 3 over a over q, and you can just change the order of things and put them in their natural ordering. So you just have n over n0 minus a over q plus a over q here, plus 2a over q minus a over q. And the sum of all of that is a closed expression. Now, what will be the total contribution of the error terms over here? So if you just could put them outside the curly brackets when you sum, if you could put them outside the curly brackets, then their total contribution would be tiny. It would be at most 0.01. However, there are a couple of cases in which this tiny thing could be dangerous. You see, it could make things overflow here or go under. But that will happen only the unexpected overflow and underflow will happen only if this expression here, n over n0 minus a over q times delta, is very close to 0 or 1. And that will happen only if delta is congruent to A inverse or A plus 1 inverse modulo q. So it's really only 1 over q of all cases, and you can deal with each of them individually and figure out the difference between their predicted and actual contribution one by one. So, done. And how quickly do you get done? Well, you basically get a closed expression plus some tiny time that you spend with the overflow and the underflows here. And so that the time per interval of this length, whatever delta 0 will be, that you will take will almost be constant. It's just that there will be a fair number of such intervals because the interval cannot be bigger than this. So you will need a fair number of intervals, and the total number of intervals you will get will be roughly x to the 1/3. Now, of course, I lied slightly because this will not quite be the case. But you can always fix this because you can always do the Finite approximation. So for every big Q, and in particular, it turns out to be wise to choose Q about, it's a constant times, what was it? It's precisely this thing here. What was the length? Yes, n0 over. So we can write n over n0 squared is equal to, it's almost equal to a over q plus of, in fact the constant is less than 1 q over q, and that is good enough. This is not too big. This gets treated in exactly the same way as this error over here. In fact, it will be of roughly the same size. And so this works out. So you're done. You're done with the subinterval. So this sum for n between, say, n0 and n0 plus roughly this q. So, but how big is q? Well, once you sum things over, you get x to the 1/3 intervals. Total time of x to the 1/3 plus epsilon. So this is the end of the proof of proposition 2. Oh, proposition 1. So for proposition 2, as I said, you would need to make this proof worse. Well, you get it to be nicer and more conceptual, but in more time. You end up splitting not just into intervals, but also into sub-arithmetic progressions. And in the intersection of each such interval and such arithmetic progression, the function, fractional part of, turns out to have become linear, literally linear. Linear in the reals. But then that carries over when you want to do things like circuit complexity, because linearity is some sort of very abstract thing. much more so than going and checking for overflows and underflows. So that works out nicely that way. But yes, it's very frustrating that we can do things modulo 2, but we cannot do things modulo 3 quickly, or modulo 5. If we could do things in the same time, modulo 3, modulo 5, and so on, we would have a general algorithm. Why is that? An algorithm that would work with no assumptions in time n to the 1/3. Why is that? It's because all we need is an algorithm that tells you whether there are any prime numbers in an interval. And if there are any prime numbers in an interval of length at most n, then that number has to be congruent to something other than 0, modulo some small prime up to size log n. So if this thing that we would have been able to do modulo 2 could be done modulo every prime up to log n in about the same time, we would be done. We would have an algorithm for finding primes deterministically without any assumptions in time at most n to the 1/3. It would still be very far from good. Good would be log n to a power, but it would be better than we have got. So this is one of our main frustrations. So that there is still a lot of work to be done, but and it's unclear. Maybe it will turn out that we have been frustratingly close to the goal, but at least it should be an object lesson in several things. So I would like to take the theme of, well, if you compute something with error less than 1/2, you have computed it if you knew it was an integer. I would like to take that very seriously, just as people do intend that standard joke about definite analysis very seriously. And also, I think this really shows how some ideas, some very combinatorial methods in analytic number theory carry over to a computational framework that was not imagined at first when these things were being done. So, that's the end of it.
Okay, thank you. Are there any questions?
So as part of your approach, you computed the sum of the divisor function.
Yes.
Correctly. Does the argument generalize at all to computing sums of other arithmetic functions?
Sort of, but it takes more time. That's a problem. You see, if you wanted to compute the number of primes modulo 3, you would end up having to compute the sum of tau 3 of n. And that would no longer be a hyperbola, it would be the number of lattice points under a hyperboloid in 3 dimensions. And that takes much more time. But, so, this is, I imagine that this sort of thing that works for the hyperbola would work also for the circle in an analogous way. So I would imagine that this sort of thing will be able to tell you the number of lattice points within a circle in times less than n to the 1/3.
I was vaguely wondering whether you can say anything non-trivial about finding a sum of 2 squares close to n. Because then there's a trivial argument that gets you quite good. You basically just take the largest square less than root n, subtract that off, and then take the largest square less than the error and subtract that off. That gives you a sum of 2 squares within n to the 1/4 of n.
Aha, that's interesting.
So the trivial bound is going to be harder to beat.
That's very interesting. I haven't thought of that, no. But that's an interesting problem in that sense.
Any other questions at all?
Well, though it's, I mean, because the squares there will be, all right, we will have to look at a board and write it out and see what the trivial bound will really be. But
I assume you can test whether something's a sum of 2 squares quickly. I don't know.
That's also a good question. It's well, it amounts to. Let me see. What does it amount to? I mean, factorization is hard, so you don't want to think about factorization in the Gaussians. But I would hope it doesn't take too much. I don't think it's a trivial problem, but I would have to look it up. I don't know it off the top of my head. Whether something's a difference between two squares, that can be, is that equivalent to factorization? Yeah. And that's definitely not easy. Well, let me see. Well, that will follow from factorization, but it's not we would have to look. I'm sure other people have done this before. I do not know the answer, even for the difference between two squares.
One of Fermat's methods.
Hmm?
One of Fermat's early methods that
Early methods for what?
x minus y times x.
Yes, exactly. But there's something he used empirically to, yeah. But I do not know whether it can be tested quickly.
You mentioned about the intersection between the arithmetic progression and some other set, and I didn't catch you very quickly, but you said that the floor function was linear over this intersection.
Oh, an arithmetic progression and an interval.
Yeah.
It's just that, I mean, the way to make this proof worse, as in more robust,
Yeah.
and it's to focus not just in sub-intervals, but you subdivide each sub-interval into arithmetic progressions. And then you look at what's going on on each one of them. They would roughly correspond to congruence classes modulo Q, but not pi. It's a bit more complicated. So the paper is written as if this were a refinement of the more robust thing that came thereafter. That's not how it was historically. So what I have given is more in the historical order, but it's not very important. It just feels more natural for me to present things this way.
No,
Yes.
there are further questions.
The proposition 2, does that use the same sort of idea?
Yes, that's what I just said. So you make this proof more robust, worse, and then you just do it, and it carries over. Proposition 2, I mean, it's the circuit complexity of this funny polynomial is such and such. Well, I mean, there's some hard work and good ideas involved, but basically it's just what I just said. You make this a bit more robust with worse bounds, a bit more abstract, and then you do it.
All right, very good. Well, there's a second talk at 3:15, I think. Is that right, Frank? But let's thank Harald again.